So start with the second and fourth order low pass butterworth filter. First of all, you know that actually we are talking about the even order filter, right? And order means what? Order means the set of filtering layers. Reflect. You have the reactive components, right? So that filters the signal. So how many layers are there? That is indicated by the order. So if we have the second order, that means we have two filtering layers. And if we can duplicate the structure, then we'll have the fourth order low pass butterworth filter. So these are the active filters, you know. Active filters means apart from filtering, it have the capability to amplify the boost of the quality of the signal also. So you already have a good understanding regarding the basic filters. You have completed those experiments in your basic electronics also. So it is just revision of those concepts what you haven't got there in the basic electronics. So anyhow, we are going to start with it. So you can see the circuit here. So this you have the input you can see and the output box you have, right? The function generator we have. And we have provided the type of signal. This function generator will provide you the type of signal you select, whether it is a triangular or a sinusoidal or rectangular, you can see, right? So that we can select from here. The basic things you already know. You know the working of the multisim, so you can select the frequency and the amplitude of the signal. Okay, right? So those things are here. We'll provide as input to this through this function generator. So this now here we have basically, if you can see, we have this RC filter, you can see, right? And we have the op amp. Now this op amp here will be the amplifier, operational amplifier, that will amplify the signal which you are going to provide as input. So after filtering, it is going to be amplified by the help of this filter, this op amp. And you know the pin diagram of 741 op amp, right? So pin number 1 and 4 for your 6 for output, and 2 is inverting one, 3 is non-inverting one. So all those things you already know. So here basically this capacitor, which is very important, which is actually this is responsible for filtering activity. Okay, and this, if you can see, this will be your, this particular portion is your second order low pass butterworth filter, second order butterworth low pass filter. Now here the output, whatever the output will be there, what you will collect, right? So this, if you see, after this particular point, this stage, if you see, so here this output of this first filter will behave like an input for the next one, right? This is the cascaded structure. So output of the first one will behave like an input for the second one, right? So it will do the amplification definitely, but apart from that, some sort of noise will also be added by this one, because every electronic component adds some amount of noise, especially the amplifier, you know. So filtering will be there, but after that some amount of noise will also be there. Further, we'll have the next layer of filter to remove that particular noise especially, and to boost up the quality further, because maybe the quality what you have got here is not up to the mark. Some amount of error is possible, and more amplification may be required. So here we have the next layer, which is the extension of this one. We can say we will duplicate this one here. So this is your second order butterworth low pass filter, and this is your fourth order butterworth low pass filter, right? So so you know this, right? Now we need to run this one, and we have to see the output at various stages. So you are very much familiar with the system, what you have to do. So the circuit is already saved. So you have to make the circuit, you have to save, and then you will have to provide the input. You have to select the input, and then you will have to run, right? So when you will run, then it will, after processing, will give you the response, that what is the response of the filter. Okay, so here, so we can see the response here, right? We have the box that will indicate the graphical view. So we can see, this is the graphical view for the first one. You can see XBP2, this one. Yes. So we can compare very easily, we can compare these two, you can see, right? So smoothness we can see. Definitely the property of the Butterworth filter will be definitely maintained, that you can see it will have this tape type of behavior. But you can see the smoothness you can observe. Why? Because this is the output for the second one, then we have the fourth order low pass Butterworth filter, and so we have the smooth curves here and here both, right? So I suggest you to take the snapshot and try yourself this particular experiment and go through the basic, because you are now, I guess, in fifth semester, and these things you have already covered in your second semester. So you please revise we have discussed the basic things regarding this, but for have a good understanding, you please refer the concept what you have developed in the second semester also. So, and this is the plot, as I told and this is your circuit. Please have a snapshot of this and try yourself. And you know that the output always depends on input. When you will vary the input, definitely the output will also vary. So this is the input you have tried for 100 hertz and amplitude 2 volt peak to peak, right? You have taken the sinusoidal input. You can apply CRO also to see the nature of the signal, and at various stages the behavior of the signal, when it passes through the resistance, the capacitor, the filter that is going as input to the op amp, and then after passing through the op amp, that amplification will be there. So all those things you should check definitely, right? And it will be better if you show all those diagrams, the step diagrams. So this is all about your second and fourth order Butterworth low pass filter. If you have any query, please ask. Okay, if you don't have any issue, no problem, you try yourself, and if you feel that you need to discuss something, feel free to discuss. And next we'll have to discuss about the signal sampling and reconstruction. The signal sampling and reconstruction, so we are going to start that one now. Next.
Sir, excuse me, sir, you're not audible.
Okay, so now we are going to start the signal sampling and reconstruction. So basically, we have three methods of sampling. We have the natural sampling and flat top sampling, sample and hold we are using, right? And for that, we have to keep in mind that Nyquist criteria should be satisfied. Now, Nyquist criteria means what? That you have the signal sample, right? The signal of you want to convert the signal into the discrete signal, right? So what you have to do, you will multiply the signal, right? Keep in mind, multiplication and convolution are similar things. So I'm talking about the multiplication. So you'll multiply the signal with the train of pulse. So definitely that train of pulse will have a particular frequency. That is one thing. And when you talk about the signal, the signal consists of so many frequency components. So the component which is having the maximum frequency, that is the maximum frequency component of the massive signal will select, right? And we have to keep in mind that the the time period of the signal sampled, right? The signal, the massive signal which is going to be sampled. So time period of that one, if say it is TS, okay, if it is TS, so the time period of the sampling, the signal, the train of impulse, the time period of the train of impulse should be less than to that of half of TS. Okay, at least less than to that of half of TS. That is your your if suppose sorry, if tm is the, say tm is the, I told you in another way, if tm is the maximum frequency component, sorry, okay, you have a signal that will have various time period, various frequency components will have. So the maximum frequency component will have minimum period, right? Maximum frequency component will have minimum period. So if tm is the minimum period of the massive signal, keep please note down somewhere, tm is the minimum period of the massive signal. So ts, that is the period of the train of impulse. So that should be less than half to that of Tm. That is, Ts should be less than or equal to Tm by 2. So this is your Nyquist criteria in that time domain. And in the frequency domain, it is just reverse. It is just reverse. That sampling frequency Fs should be greater than or equal to, okay, greater than or equal to 2 times to that of Fm, where Fm is the frequency component, maximum frequency component of the massive signal, maximum frequency component, because the maximum frequency component will have minimum period, right? So this is the Nyquist criteria that should be satisfied. So here we'll start with the single tone signal. Let's say we have a single tone signal, so we have to select the signal from signal source. We'll go to the sinusoid and we'll take one sinusoidal signal, okay, of some 1 hertz signal. If we'll take, will basically follow the structure. This is the condition, right? This sampling frequency should be greater than equal to 2 times of the FM maximum frequency, and you can see this relationship. So you have to take the signal and have to multiply it with the train of impulse. Okay, so you have to multiply this with the train of impulse. And you have to set the value of this one. So this is the train of impulse, right? Fs, and this is your Fm, right? Massive signal frequency. So it says that, if you can see the relation, it says that the Fs should be greater than or equal to 2 of Fm, twice of Fm. right? At least equal to or maybe greater than that. So if FM is of 1 hertz, then Fs have to be at least 2 hertz. So this is your sampled version of the signal. Now it have to be at least 2 hertz. It can be more than that also. So accordingly you can see the appearance will be better. Why? Because it gives you the value of the interval after which you'll have to select the signal. So previously you have selected the signal after an interval of as a frequency of 1 hertz. Now it is 5 hertz. So definitely you are going to take the signal at an interval of 1 by 5 times of the time period. So you'll have more data, right? So that means what the signal frequency, if you understood, so it should have a higher frequency value as compared to the massive signal. There should always be a high frequency value as compared to the massive signal, at least 2 times. So this is your sampled signal. Now, if you want to reconstruct the signal back from this one, what you have to do, you require a capacitor. So capacitor will be charged up to this point. Okay, you can see the cursor. The capacitor will be charged up to this point, and then when the signal will drop down, it will start discharge. So it will go down, and again when it will reach here, it will again charge. So likewise, it will actually connect the peak points. It will connect the peak points. And actually, we are talking about the integrator where we have the resistor and the capacitor, so that will charge up to the peak point and then discharge and again charge up to the peak point. So likewise, it connects all the build the peak points of the this signal, which is the input. So this is basically integrator, which is a low pass filter. So we need to have a low pass filter. Low pass filter is nothing but the integrator. So we are going to use the low pass filter here, the integrator here, to reconstruct the signal back. Okay. Okay, so as I told that, oh, to reconstruct the signal back, you need a low pass filter, right? That's okay. But what should be the cutoff frequency of the low pass filter? How will decide the cutoff frequency of the low pass filter? Any idea? So low pass filter, you will have here in this section. We'll go for IR filter. It's always good to use a higher order filter. So we are going for Butterworth and we're going for low pass filter. And actually the cutoff frequency depends on the maximum frequency component of the master signal, because you want the signal to, you want the exact signal to extract, right? So you don't want to lift some portion of the signal. So that's why the carrier, the filter cutoff frequency should allow only the master signal to pass. So the frequency should be greater than the maximum frequency component of the master signal, slightly greater than. So if it is 1 hertz, here you can see, so we'll make it like 1.2 hertz, and that will be sufficient because we want only this signal to pass through the filter. So you can see that we have the signal, but it is a time varied version, right? Time varied version that is allowed actually. So it is because uh, we have the signal that is coming here directly and one which is passing through this one, right? And the frequency variation is also there. Here if you see the frequency is of 10 hertz, here it is of 1.2 hertz, so definitely the effect will be there, but we are able to extract the master signal back from this one, right? Now what we have to do, the objective is to extract the exact signal and to check whether it is appearing as an envelope or not, right? So here, first of all, what we can do, uh,
Sir, you are not audible.
Okay, yeah, yeah. What I was saying that this is your natural sampling, and here I'm going to show you the frequency domain also representation. So you can see this is your frequency domain representation of the signal. So this actually this red one and blue one is overlapping. You can see here. So this is your sampled version of the signal and the massive signal. So you can see that actually they are overlapping and they have exact match. There is a variation in the magnitude only, and these are actually because the frequency of this the delta function, that the train of impulse, if you see, it is of 10 hertz, right? So that's why you have fc plus fm value 10 plus 1 and 10 minus 1 values, they are 9 and 11. So this is the, you can say the residue of this one, right? So you have this particular value of massive signal along with the carrier signal in the frequency domain. So it shows that your mod this sorry, the sampling is correct because it is overlapping in this region. And one is what? One is the frequency of the actual massive signal under consideration. Now, here what we can do, if we just change uh, this particular signal with train of impulse, you will have this, you can see. So here you can see one thing, that now previously we are talking in terms of the frequency, here we are talking in terms of time period. So I told that the time period have to half to that of the minimum component period. So this is 1, right? Frequency is 1. So time period will also be 1, and half of this one is half, right? So it have to be less than half, less than this. This is the maximum frequency component value, that is frequency is 1. So here it have to be less than half, and so it is 0.4. So when you will take 0.4, you will have this type of relationship. Further, if you will suppress it, the value, so this is, you can see the sampled version of the signal. You can compare this plot, okay, with the previous one, what you have obtained in both the cases, what we have, right? And as we are going with the values like 0.2 you have taken, if you will take 0.5, let's say for example, So you might have obtained that here. If you will, if time period, you will gradually suppress zero point 0.5 to 0.05. We have seen at this moment. So previously it was zero point 0.5, now it is 0.05. So you have more defined diagram, right? You can see here. So this is your natural sampling, right? Then we have the next. We can apply the sample and hold circuit here also. It's shown here in the diagram in the manual. I guess it provided to you. So you can use the sample and hold circuit also along with the train of impulse. Along with the train of impulse. So this is sample to hold circuit output. You can see. So there is a sampling, and it is to be taken in the various steps, right? So that's why we have this variation, which is sampled signal, as used there simple and hold circuit. And then again, hold means the low pass filter. When you will apply, you can have the massive signal back from this. So here you can see the sample and hold circuit output represented by red in color, and blue one is actually the reconstructed signal back from this. So you can see. So that's how we can do the sampling and reconstruction. So you have all the three methods with you. Now I'm going to provide you the system so that you can start your performance. And if you have any query, you can ask also in between.